This is a review of what we call mechanical energy. And how changes in kinetic and potential energy are related to it. So basically the mechanical energy of a system is the sum, or the total, of the kinetic energy due to motion or speed, and the gravitational potential energy, which is energy due to height above the Earth. Gravitational potential energy. And we have a couple of formulas that we use to describe these. Kinetic energy, which is 1/2 mv squared. And we have gravitational potential energy, which near the surface of the Earth can be calculated with this handy formula, mgh. So, mechanical energy often comes into play when we look at the trade-off between these two forms of energy, kinetic and potential. If you imagine an object that is falling, let's take a ball, for instance, and we'll drop that ball from a certain height. Let's pick a height of 8 meters. Well, as the ball falls downwards, it begins to accelerate, picks up speed. Initially, the speed is 0, but as it falls due to gravity accelerating, it picks up speed. But as it picks up speed and falls, it also loses height. And so you can see how kinetic energy, which is based on speed, is increasing as it begins to accelerate downwards. But gravitational potential, which is based on height, is decreasing. The total amount of energy, though, remains the same, and that's the conservation of energy law that we're all familiar with. That, of course, is with the understanding that we are neglecting minor changes due to things like air resistance and whatnot. So we're assuming that any loss of energy in this particular kind of a scenario is very, very minimal, almost infinitesimal, and not worth worrying about. So it's a trade-off between speed and height. And so it's kind of like a dance that's played. If we consider the initial conditions of this ball, we could give the ball a mass, but as you'll see, the mass often isn't even important because both of these equations have mass in them. What often happens is the mass tends to divide out of the equation and not even be important at all. So let's not even worry about the mass, but let's talk about what's happening at the top of the scenario and at the bottom. At the top of the scenario, we have a velocity of 0 because it hasn't had any time to accelerate at the instant it's dropped. But we certainly have a height of 8. At the bottom, the height has become 0. So you can see that the height has dropped. I'll put over here. Height has dropped. It is diminished. But as a trade-off, the speed will actually increase. All right? And we don't know exactly yet what this speed is. We're going to set up a problem to actually solve for that. But the speed will increase. So we know that there will be a velocity here where there was none originally. And so velocity is going up. And you can see how this trade-off is happening. At any point in this scenario, a very important thing is taking place. And that is the law of conservation of energy, which says that the total mechanical energy, mechanical total, before or at any one place, is always equal to, let's call it 1. At any position 1 is always equal to the total mechanical energy at any other position in the entire scenario. And we can choose where our 1 and 2 will be. We're going to look first at the top and the bottom. Those are obvious places to start because we have nice zeros there that make things easy. But this is true. This statement is true anywhere. You could compare, a position 3 meters high and a position 6 meters high, and this statement would still be true. But let's go ahead with the top and the bottom. All right. So the total mechanical energy at our position 1, or the top, would be the kinetic energy at position 1 plus the potential gravitational energy at position 1. All right? And then, because that's the total, that must be the same elsewhere. And so we can put position 2 and describe it the same way. What will change are the amounts of the individual kinetic and gravitational energy, but the totals will be the same. So we're describing this side as the top, where the ball is beginning to drop, and we're describing this side, the bottom, where the ball is just about to hit the ground. Just about to hit the ground, moving quite quickly. So if we continue this on, we can replace these symbols with the actual formulas that are used to calculate them. So this would be 1/2 mv squared, and it would be the initial speed at position 1. And here we would have mg, and we would have the height initially, position 1. Then we would go over here, and we would have the kinetic energy at position 2, 1/2 mv squared. And then we would have the gravitational energy at position 2. So you see how this is all notation. We haven't actually put in any numbers or looked at anything yet. We're just setting up the scenario. This, in a sense, is the mathematical version of the law of conservation of energy that we would say in English. Matter is not created or destroyed, can only be changed in one form or another. The total energy at one point has to be the same as another, and so on. This is the mathematical way of describing it. So now that we've set it all up, we can use this to solve virtually any kind of problem that involves mechanical energy. Let's go back to our ball. The ball was 8 meters high. So the only bit of information that I have, right, now what would be the initial speed of the ball? Well, if it's just about to be accelerated, it would be 0, because as you drop the ball, it has not yet had any time to accelerate. So it starts off with a velocity of 0. And g, I know, is 9.8, if I want to put that number in. Notice that we're using the magnitude of g. We're not putting a negative sign because direction doesn't matter with energy. Energy is a scalar value. Direction is irrelevant. That's what makes energy so convenient to work with. And then, of course, h1, which we said was 8 meters high. That was the initial position. Later, we want to compare at the bottom. So at the bottom, we would expect that there will be a speed. We don't know what it is yet, but it will be there, so we'll keep that the way it was. But guess what? Now all of the height is gone. Now remember, we're using the bottom of the cliff as our 0 line, right? When you're doing gravitational energy, the lowest point in your scenario is usually where you consider 0 to be, and then when you get all your other heights, they're all measured from that spot. So we're going to call the bottom 0, and of course that would be a height of 0, right? Okay. This reduces to 0 plus, and if we do 8 times 8, 64, I think that would be 78.4 times m. Put the m over here. And over here, this is now a 0 because of the, oh, I'm sorry, no, my mistake. The gravitational energy is a 0. But this is still 1/2 mv squared. We haven't really figured out anything about that yet. Here is where there's a 0 because we're multiplying by 0. So you can see what we're saying in this little mathematical paragraph is that the total amount of energy before is all gravitational. Here it is, all gravitational. However, at the bottom of the scenario, we can see that whatever energy we have is going to be all kinetic. So we've done this trade-off. We've traded what was once height, gravitational energy, we turned it into speed. And so now this is going to be fairly easy to solve. There's a couple of things we can do. The masses can be divided out of both sides of this equation, and basically we need to multiply both sides by 2 so that we can eliminate the half. So this would be 6. So 156.8 equals V2 squared. And then if we take a square root of that, we can get the answer. And that would be about 12.5-ish meters per second as the velocity at the bottom. Now we've used this little expression or equation to figure out what the speed was. But let me point out to you that everything you would ever need to know is in here. Masses are here. Heights are here. If the question asks you for a height, it will show up here. Speeds are here. And in fact, even if you wanted to drop this ball on the moon, a question could be made up on the moon where you could solve for the value of g on the moon and not even use 9.8. Any of the things that could be asked of you are present right here in this scenario. And so that's the reason why I like to use it, because it doesn't matter what the question asks for. If you start with this introductory statement, your answer will emerge in the math, and whatever's left over at the bottom will automatically be the thing that you're looking for. So this setup is very convenient. You don't have to play the game of trying to figure out what you're looking for and what you need and where you should go. All right? So that's how mechanical energy can work. And notice that mechanical energy is a vector, and it has direction has no effect on it. For instance, if we didn't drop this ball, but if we had taken this ball with an initial speed of 0 and then somehow attached a rocket to it, and the rocket ship carried the ball over here and down and back up and then around over here and over here and over here and eventually dropped the ball somewhere down here, well, then the distance between its initial starting point and its finishing point is still 8 meters. It has still changed its height, 8 meters, and so it would still be exactly the same answer. All right? That's assuming that this rocket ship didn't accelerate up or down. I suppose a rocket is a bad example. Somehow a magic ball that could fall along this path. The point is that direction doesn't matter. If you shot the ball upwards and back down, like this, that would be no different than if you threw the ball straight down at the same speed. As long as the initial speeds upwards and downwards were the same, direction doesn't matter. That's why we like to use energy when we're dealing with stuff like this. It's much simpler than some of the kinematics that are involved. So there is the story, and that's how mechanical energy can be utilized.